So today we're going to continue our discussion of covering spaces. Last time we introduced the idea of a covering space. I'll recap that with you now, and the goal is to be a little bit more rigorous in our discussion of some of these properties of covering spaces. But I encourage you to review the last lecture that gave kind of an introduction to this idea of covering spaces. But just as a reminder, a covering space is when you have some projection from some covering space x bar onto some space x. And often we think of there being some base point, x naught being some base point. Or sometimes I'll just call it little x, maybe x naught. And so I'll also keep track of the base point in my cover. P will send the base point of the cover to the base point of the space. So it's some projection where there's some open cover, a collection of open sets that covers x. So if you cover x with open sets, there's an open cover such that P inverse on any one of these open sets is homeomorphic to the set itself. So let's look at a quick example of this. Our space X could just be a copy of the circle with some base point here. I'll specify the base point by putting a dot there. X naught. And you have several possible covers of this, but here's one cover. This guy that's going to loop around three times, where you can think above this base point there are three base points. You can specify whichever one you want, but I'll just call them three different names like x1, x2, x3 are all over this base point down here. They all map to it. Another way of thinking about this space is it's just one big circle where you pass through the base point three times when you go around, or three copies of this cover of the base point, where maybe this is base point, the first one, the second one, and the third one. But the idea is this projection map P, so this is my covering space up here, x tilde, P just has it so that as we travel around, that maps to traveling around. So traveling around the circle once would actually take us around the circle three times. Because just going from this base point to this base point is making an entire loop. From this base point to this base point takes one loop. So going all the way around, or all through all three base points, takes us three times around the circle on bottom, right? So let's try to see what this has to do with this open cover definition. Well, there's a couple ways you can cover the circle with open sets. Here's one simple way. Take each open set to be just like a little bit more than half. So like here is one open set, and the other one, let me get a very different color. So like get some green. And you can take this to be your other open set. For it to cover, they need to overlap a little bit. Then you map the red up, and you see that red maps to something like this. It's like this portion, and this portion. Whereas that green maps to this portion, and this portion. And this red is just a little arc that's homomorphic to that little arc, or that little arc, or that little arc. So each red arc is homomorphic to the arc above it, and each green arc is homomorphic to the arc above it. Meanwhile, this entire circle has preimage an arc. So the entire circle as a whole is not homomorphic to its preimage, which is just one arc. But each portion of the circle is homomorphic to what's above it. Are we happy with that? Okay. So locally, you can't really tell if you're down here or up here. But if you zoom out, you can make, here I'm just going around the circle once before I get back to this base point. Whereas here you go around once and you cover 3 different base points, right? So globally, it's different on top, but locally it looks the same as on bottom. So that's the idea of a covering space. And we saw lots of examples of covering spaces. I mean, this is one example of a covering space. What's another covering space for S1 for the circle? Is that better? Maybe what's happening is my hair is getting in the way. My goodness. Is that better, maybe? Yeah? Okay, let me know if my hair makes too much noise. Okay, what's another covering space of the circle? Yeah, so like in the extreme, you would have R1. So you could have a helix like this that goes on forever. So you could have a helix like this that goes on forever. Let's make sure we draw this right. Forever. So that's just a depiction of the real number line that's been wrapped around as a helix, sitting on top of the circle down here. Submap P. Well, now there's infinitely many base points that get mapped to this base point, possible base points, right? And you can choose to specify one of these as the base point that you'll be working with, but just by looking at this, there's infinitely many correspond to each of the integers. You know, there's like 0, 1, 2, 3, -1, that all get mapped down here to this base point. Or you get a helix wrap any other number of times. So here it was 3 times, nothing special about 3. You could have had a helix that wrapped around 2 times or 3 times or 4 times or whatever you want. So sometimes I just kind of start going and I see what I get. So looks like that one is 1, 2, 3, 4. 4 times. So this is the same as a circle where there are 4 different base points that all map down onto your S1. So each of these 4 points, whichever depiction you prefer to think about it as. I drew the spiral backwards, didn't I? No, this is right. If I'm going this direction, counterclockwise, I'm going up the spiral. Yeah, good. Okay, so whichever one you prefer to think about. Now, what I want to make the point here is, you know, here you have this guy wrapping 3 times. Here it's 4 times. It's always going to be a nice integer copy. And even if you're not just dealing with the circle. So if you come back over here, remember our example of a wedge of 2 circles we talked about last time. So maybe one of these we think of as being generated by some A, and the other one by some B. So here A is going out, here B is coming in, here B is going out, and B is coming in. Then your covering space will locally look the same. Lots of things we could draw, but here's one of them. Say locally, yeah, it should look something like this. So we could draw it to look like this, where maybe this is A, B, B. And here are the 2 points that both map onto your base point. But what I want to make the point is if I cover this with open sets, so I'll cover this little X portion with one set, that's homomorphic to these little sections, Because notice here you have an A out, A in, B out, B in. Up here you have an A out, A in, B out, B in. And then again you have the same thing up here where you have another little X, where you have A in and A out and B in and B out covering an X. And here you can cover this portion with like some red portion, and that's going to be homeomorphic to these guys. And here I can cover this with some green guy that's homeomorphic to this guy and this guy. What I want to make the point is no matter where you're at, if you're in this yellow section, you have 2 points above it that map down to it. You know, like if you're right here, the B coming in on the yellow, then the corresponding points on top would be like this point right here, and B coming in this point right here. Or if you're over here in this red, you know, middle of the red, I'll draw like a little triangle there, you have 2 points above it, this point and this point. No matter where you're at, the number of pre-images you have, the number of points in your pre-image is always equal. It doesn't have to be 2. You know, this guy would also be 2, but here would be 3. You know, if you're like right here, you would have 3 points in your pre-image. Well, this one would be 4. This one's 4, right? You would have 1, 2, 1, 2, 3, 4 points in your pre-image all get mapped there. And if you pick a different point, it would also have 4 points in the pre-image. So that number is constant. Why is the number constant? Well, the number is constant because the number of points in your pre-image has to be an integer. And as you move, it should vary continuously. But the only way for an integer to vary continuously is for it to be constant. Right? So I'm just saying the number of points in your pre-image is constant. And that number of points I'm going to refer to as the number of sheets. So here this is a two-sheeted covering space. Here we had this first one was a 3-sheeted covering space and a 4-sheeted covering space. And you can also have examples where there's infinitely many sheets, right? Infinitely many. So for example, one infinite cover of this, one cover of infinitely many sheets, would be this cover. There's the universal cover, but it doesn't even have to be the universal cover. You could also have, last time we talked about this cover. That's another covering space of the wedge of 2 circles. Where locally, it looks exactly the same on top as on bottom. If you're by this point, this little x is reproduced at each of these, B in or B out, and A in and A out. If you're over here, it's like you would be on one of these loops. If you're over here, you would be on one of these stretches. And there's infinitely many preimages, you can see. Good? Okay, so that's the idea of a sheet of a covered space. We also talked last time a bit about finding the fundamental groups of these covering spaces. And the way we did that last time is we said, well, to find the fundamental group, let's think about, if this is my space, X cover of X, let's think about what is the induced map of the projection on pi 1 of this fundamental group on top, and then you can pick one of these points, say this one, to just be your base point. X naught tilde. What the induced map of the fundamental group means is we're going to look at loops when they get mapped down, which is exactly what this labeling is doing. So I labeled this A because when I map that arc down, it gives me A. So putting these labels here means I'm really thinking about the induced map of pi 1. And last time we talked about strategy to find this, where you can just select a maximal tree, which in this case is just a single arc, and then read off the words for the other remaining arcs. And this would give you, it's generated by, for the first arc, A squared, going down the tree and then up A, and then A, B, and then down A, up B inverse, A, B inverse. But there are equivalent presentations as well. So if you wanted to, for example, you could find the inverse of this guy. It's BA inverse. Multiply by him, you cover B squared. And then if you have B squared, you can show that this is equivalent to just A squared, B squared, AB. So you can have several different presentations of the same group. Whichever one you choose, it should have 3 generators. Okay. What I want to do is justify that this induced map on pi 1 is really the same thing as just pi 1 of the covering space itself. So this is what we need to justify today. What we calculated here is actually the induced map on pi 1. What we need to stop and convince ourselves of is that this, when you apply P star, it doesn't change the group at all. So I want to do that. There's one other thing I want to do. And the second thing I want to do is just note there's a relationship between this group structure and the sheetedness. And maybe it's easier to see it in one of these examples. So like come here. Here, if you think about this guy on bottom as being generated by, say, A, then the induced map of the fundamental group of the cover at whatever base point you pick, let's just do x1, will come out to be, well, a loop up here is equivalent to 3 copies of the loop down here. So it's A cubed. Now, in a second, I'll justify not only is this P star of pi 1, this is actually also equivalent to just pi 1 of the universal cover. So take that on faith for now. But then, what can you tell me about, oh, and then down here on bottom, of course, pi 1 of just the space X is just Z generated by A. So it's just the free group with one element, or Z, the guy generated by A. But what do you notice about the relationship between these two groups? Well, he's a subgroup of this group. And when you have a subgroup, you can calculate something called the index, right? So the index is just looking at what is, so often we'll denote index something by, like, if you have the group A and you want to know what is its index with A cubed. And then maybe you put this in brackets. Is this how I typically write index with G and H? Yeah. So what would this index come out to be? Do you know? Just 3. So this is essentially like Z mod 3Z, right? This is like comparing Z with 3Z. And the index between those is 3. And this was a 3-sheeted cover. So I'll just point out, I don't think we'll necessarily prove it. It's not hard to prove. You just mainly construct a bijection. But the index is equal to your number of sheets. So we have a relationship between the geometric interpretation of how many sheets a cover is and this algebraic fact about the index of the subgroup. And maybe it's not too hard to believe that this is an index 2 subgroup of the group for this guy, where your pi 1 of your x is just the group generated by A and B. So maybe take a second to verify that this is in fact an index 2 subgroup. But I want to prove this fact. So we're going to need to build up to it. So a couple things to build up to along the way. First, so let's list some facts along the way. And these are much more powerful facts we use for many other things as well. The first I'll mention is called the unique path lifting property. Which simply states that if you're given a covering space, and I'll record my base points too. So I specified some base point. If you're given such a cover, and you have some path, I'll call it gamma, which would be a map from, say, 0, 1 into x. And I want it to be a path that begins at my base point, so that gamma of 0 is x naught. Then there exists a unique lift, a unique gamma hat, which is a map from 0, 1 into the covering space, such that two things happen. This cover begins at your specified base point, x naught lift. You can instead start at a different base point, but there's only one from the other base point as well. And the projection of the lift of gamma is just gamma. This is saying it really is a lift of gamma. So let's see why this is true. Let's prove it with this example. But the proof is going to be compelling that you'll see it's true in general. So let's begin with just some path that begins at your base point. And you can make it whatever path you want. So I'll make it the path maybe that goes around A once and then goes around B once. Good. So it starts off going around A and then it goes around B. It starts off here at my base point x naught. Now we have specified which of these points up here is my x naught tilde. So you decide, whichever one it is. You've specified some base point. Let's say it's this one, x naught tilde. Then what I want to say is that we call locally, if you look at just a little neighborhood of x naught, that little neighborhood around that point is homeomorphic to the neighborhood around that point. This is the definition of being a covering space, right? Okay, what does that mean though? Well, since there's a homeomorphism here, like if this is some neighborhood U, or call it U1, since I'll have several of these neighborhoods, this is homeomorphic to P inverse. This is P inverse of U1, which means you actually have a map going this way, which is just P inverse restricted to U1. It's a homeomorphism, so you have a bicontinuous map. So you can map things up within this neighborhood, just within the neighborhood. So do it. So just map up this first little portion of your path to wherever it goes inside the neighborhood. Okay, so at least now it's like this, where this path begins is entirely specified. There's no freedom at all. It has to be sent to the course, but wherever this homeomorphism takes it. right? So what do we do next? Well, now we've reached the end of this neighborhood, so you pick some other little neighborhood that overlaps with it a little bit. You know, your U2. And that's homomorphic to some little neighborhood up here, right? And so now for the next portion of this path, there's no choice, it just has to map up to wherever it maps up to in U2. And you keep stringing this along, one more neighborhood at a time. So here's my next neighborhood. You know, I could have even done a bigger neighborhood than that if I wanted to. Yeah, let's get a big old neighborhood, right? Big neighborhood. And that's homomorphic, you know, to like that neighborhood or whatever it is. So this little portion here has to get sent up to that portion there. And you just keep doing little neighborhoods all along the way, right? And then you see that this path down here only has a single guy, you know, he only has a single guy he can map to up above that begins at this base point. And that's going to come out to be that map, that path up there. So there really is a unique path upstairs for every path downstairs, as long as you specify which base point it begins at. There are other paths that begin at other base points, but at this base point, there's a unique path that lifts any path down here. Are you happy with that? Is that clear? Good. Okay, this is a really important property of covering spaces, because now that you know this, you'll believe that there's a unique homotopy lifting theorem. So I'll put unique in it. Sometimes we don't say unique, but just the property is saying it's unique. It's a unique homotopy lifting theorem. Or homotopy lifting property. Which says that if downstairs you have some homotopy, so we're still given a cover, we're still given some cover P, where we specify one of the base points upstairs that maps onto your base point downstairs. You're still given some cover like this, but you're also given a homotopy downstairs. So I'll call the homotopy just f of t, where this is the whole family of maps, t going from 0 to 1. Each of these f of t's is a map from 0, 1, but there's another range of 0, 1 of the t's. So sometimes think of the homotopy as mapping 0, 1 cross 0, 1, because t is also ranging from 0 to 1, into x. If you're given such a homotopy, and you pick, and each of these will like have go to the base point. You know, like each ft of 0 will just make sure it goes to your base point for all of your t values in your homotopy. And you specify how one guy lifts. So let's say F0 and F0 lifts to gamma. So what do I mean by that? I just mean that if you compose P with gamma, you get F0. Now, we know you can lift F0 by a path lifting property, right? So this is going to lift to some gamma where your gamma of 0 we can specify is at your base point upstairs. So we're just going to use this to lift up the first map in this homotopy. Then there is a unique homotopy. Which I'll just call F tilde of t. Such that F tilde at time 0 is your gamma, and f tilde is truly a lift at all times of f of t for all t. So what does this say? This got a little bit full down here, but let's say you have some path, and I don't know, I'll make it this path, this blue path. Let's say this is my f0. Let's forget this name for now. Let's say this is my f0. I can lift that f0 upstairs to this guy that I'm calling gamma. Then what the unique homotopy lifting theorem or property is saying is that just as downstairs you have a homotopy that just shrinks this down until it's a single point. So there's some homotopy, f of t, that's just going to shrink this path down to be shorter and shorter and shorter until it's a single point. Then there's an analogous homotopy upstairs, a lift of the entire homotopy that starts off at gamma and just shrinks it down until it's just a constant point. Because this homotopy has to map onto that homotopy. Well, why is that true? This is just using the path lifting property for every single one of your f of t's. At every time ft, just lift that little path up, and this unique path it lifts to, and if you lift them all, you get a homotopy upstairs. So that's just saying if you have a homotopy downstairs, you can lift it to this homotopy upstairs. Happy with that? Okay. How does this help us? I want to prove this. And I claim now we have the tools to. So I need some more space. So let me move this over. I think I have space for this here. Proposition. The induced map. So again, we're given some covering space from, okay, I'm not going to write the base points every time, but you understand I have some base points in mind. The induced map on pi 1, and you can write your base points if you want, onto pi 1. This induced map is an injection. And if that map is an injection, then it follows pi star of pi 1 of x tilde with its base point will be isomorphic with just pi 1 of x tilde x naught. Right? If I have an injective map here, then I'm going to, this guy stays the same size. I don't lose anything. So you have an injective map. Good? Happy? So how do I prove this? Proof. To show a map is injective, you tell me, what are some of the ways you show a map's injective? Particularly a map between groups. This is an induced homomorphism. How do you show a homomorphism is injective? Those who've taken some abstract algebra. Good. We want to show the kernel of this map is trivial. That there's nothing non-trivial that gets mapped to something trivial. So suppose you have some element in the kernel. So I need a good name for an element of this guy. So I'll just call him alpha, is some element of the kernel of this map. What that means is that when you apply pi star to alpha, it comes out to be trivial. So 1 or 0 or whichever notation, I'll just use 0 here, but he's trivial. Which is saying that when you do P with alpha, it must be homotopic to the constant map. Right? So P with alpha has some homotopy that takes him to the constant map. But then, by a homotopy lifting, but then you just then you can just lift the homotopy. And so what you get is that there's a homotopy from alpha upstairs inside of, you can lift it up here to x tilde. So now there's a homotopy from alpha to something that maps onto the constant map. Well, what maps onto the constant map? The only thing that can map down into the constant map is itself the constant map. So he also must be homotopic to the constant map. This first time, this was saying this was true in x. But by the homotopy lifting property, we're saying it's also true in x tilde. Hence, we've just shown that alpha itself is trivial. 0 or 1 or whatever your notation for trivial is. So this kernel is trivial. So this map is injective. So mapping doesn't change your fundamental group. Which is all to justify this entire discussion we've been having over here about these fundamental groups. Right? Like, how do I understand the fundamental group of this space? I think about the fundamental group of this space in terms of what it maps things down into. So I'm just trying to justify these presentations. So this has now been justified. Good? Okay. So that got a little bit technical, but I just wanted to make sure we were crossing all the T's and dotting all the I's in this discussion. I think I think what I want to do is draw some more pictures. So last time, we talked about this wedge of two circles. This is S1 wedge S1. Thinking about having generators A and B. And we said that there was a special covering space for this guy. Maybe I'll need some more room. Called the universal cover. Now, this example of R here is also a universal cover. So what characterizes something as the universal cover? Yeah, to be the universal cover just means you're simply connected. Which gives you that pi 1 of your covering space with whatever base point you pick is trivial. So 1 or 0, however you denote trivial. Okay. So I want some space here with no loops. Simply connected means no loops. Right? Simply connected. So it shouldn't have any loops. It won't be like this guy with these loops or any of these with loops. And last time we just started constructing this. And we said, okay, so we need something coming out for the A and coming in for the A, coming out for the B and coming in for the B. And maybe it'll be best if I do this with a couple colors so we can kind of see what's going on. So let's do blue and yellow. I guess those are kind of our university colors. So blue is A and yellow is going to be B. And so at this base point, I need an A that comes out and an A that goes in. I need a B that comes out and a B that comes in. But I don't want them to loop back because I don't want any loops. So I must have base points over here at all these places, pre-images of the base point, other points that map to this base point. Which means at each of these, we must also have the same kind of thing going on. Okay, well this was hard enough to draw with one color. Maybe it's becoming even more difficult to draw with two colors. But we start to get this pattern that if we keep going, gives you this fractal design. So each of these are base points. And then down here, you want, okay, I'm giving up at this point. You see what I'm trying to draw. So like on a lazy afternoon, you should draw this with like incredible 6 layers or something to get a nice feel for it. But you see what I'm trying to draw here. And so forth, right? This fractal emerges. Feel really unsatisfied with it being incomplete. It's just like deeply unsatisfying. Deeply unsatisfying. Can I stop? Okay, I'm going to. Oh, I want to keep going. Some have more layers than others. Oops, my bad. And keep going, right? Infinitely much. Because if you loop around A like 10 times, then I'll be going this way 10 steps. Or if you loop around A and then B twice and then A, that's A, B twice and then A. Right? So you can start seeing how looping around downstairs corresponds to moving upstairs. Okay, I claim there's always a universal cover like this. And to show that, I'm first going to say that's actually false. So here's why it's not true, but it's only not true in weird cases. And if we can avoid the weird cases, that is always true. So what's an example when you don't have a universal cover? Well, consider this space X. I'm going to take a wedge of infinitely many circles, but I'm going to make each circle a little bit smaller than the previous guy. So I'm going to make this a wedge of infinitely many circles, where each circle is like of radius 1 over n, where your n is like greater than or equal to 1. So this is a wedge of circles of smaller and smaller and smaller and smaller radii. Why doesn't this have a universal cover? What you should think goes bad here is your universal cover, you don't want to have any loops. But also locally, it should look like what it looks like downstairs, which means you should be able to find a little neighborhood downstairs, and locally it looks the same, right? Like this little neighborhood of that looks the same. Or if you're over here, that little neighborhood looks the same. Or if you're over here, it looks the same, right? But take a little neighborhood of your base point. However small you want to, there's always going to be loops inside, because they're really tiny circles. Which means you'll always have loops inside of your covering space. So this guy doesn't have a universal cover. But this is a weird space. You know, it's like you get these loops arbitrarily small. Very, very strange space. And so as long as you don't have any weird behavior like that, then you'll have a covering space. So let me give you a few words. So we need some things to have a universal cover. So to have a universal cover, we need that X doesn't have this property. That if you take a little neighborhood, you don't have any loops. That's called semi-locally simply connected. Which literally just means, that for all X in your space X, there exists a little neighborhood, a small open set you can think of, some neighborhood U, such that all loops in U contract to a point. So the loops contracting to a point is being simply connected, but you want to say at every point X, there's a neighborhood around it with the property. That's why it's called semi-locally simply connected. There can still be loops overall. Like you can still have the circle, but if you take a little piece of the circle, everything contracts, right? So this is just saying avoid this kind of bad behavior. We also will keep, just for avoiding other bad things, our space should be path connected. And it will also be something which is locally path connected, which is a similar kind of idea that says if you take any point, there's a neighborhood around that point that's path connected. If you have these properties, then there exists universal cover. Now, there's two ways we often go about this. To prove there's a universal cover, you give a way of constructing it that's very unnatural, but then in practice, we have maybe more natural ways of constructing things. So here's the definition. Here's how you could prove there's a universal cover. Here's how you could define universal cover. You could take universal cover with base point x naught. You could define it so that the points in here are themselves just homotopy classes of paths, where you think about those paths as being well, gamma is a path in X. It's a homotopy class of a path in X starting at x naught. So gamma of 0 is going to be x naught. So this is a weird abstract definition, but you might want to take a minute to kind of convince yourself that it maps onto here. Like what is, each point on here, you specify any point. That point corresponds exactly to a homotopy class of something down here that begins at x0. So like this point corresponds to the homotopy class of everything that comes around and ends there doing a single A, right? Or like this point over here corresponds to the homotopy class of anything that goes around B and then A. So the homotopy class of things that go around B and then A. So, this definition really does describe what we have here. It's just a very strange definition. But it works because of a homotopy lifting property. So by the homotopy lifting property, these paths in X starting at x naught can also be thought of as paths in x tilde, homotopy classes of paths in x tilde starting at x0 tilde. But in practice, this is not how we construct universal covers. In practice, we construct it more like we did this one. So maybe to see how we actually do this, it would be good for me to give you a space we haven't talked about yet and see if you can come up with what the universal cover for it is. And so for that example, let's think about S1 cross S1, which is the torus. A circle full of circles, right? Where here you think there's some circle going this way, and then you have circles going this way, and there's a circle full of circles. Okay. Well, maybe before we build up to trying to understand what the universal cover of this guy is, can you give me any covering space of the torus? Can you give me like a two-sheeted cover of the torus? Here's the torus. I want some two-sheeted cover of the torus. Can you give me that?
So what I'm kind of imagining is you kind of rip it open in the middle and like kind of twist it around the second time that we join it.
Oh, yeah. So you can think cutting the torus right here. Now you just have a cylinder, and gluing two of those together would give you something like this, yeah? Where you want to know, like, what is the pre-image, you know, like, if you have some graph here, he gets mapped up above to, well, whichever, you gotta pick, there's two pre-images of that point. So you pick one, and you know, maybe it's this one, and he would get mapped up to that guy, right? Not even that far, you know, he's, you know, like that far or whatever, because going around once only gets you around halfway through the torus. So if you think of this torus, so down here, we can think about if he had gone all the way around upstairs, he would have just gone halfway around. So to go all the way around up here, you have to go around twice downstairs. So if we think about this green circle as being generated by some A, and this red circle as being generated by some B, then we have that the fundamental group of this torus downstairs, the fundamental group of X, is just the group that's generated by A cross the group generated by B, right? It's Z cross Z or Z squared. So this is the same thing as Z squared, but I want to think about it in terms of its generators. Can you tell me what the fundamental group of this cover is? Well, if this is my A, going around once around A is still going once around A. So this is still just going once around A. And you just need like this one to be the, you know, I drew this copy to show where it's cut. But for the generating this fundamental group, you just need one copy of the circle. And he stayed the same, he's still just A. But now, this circle up here is actually a B with another B. So this circle becomes B squared. So he is like, or maybe we prefer writing 2B. Maybe that's better if I'm thinking of these as generating Z. I don't know, what do you want, B or B squared? 2B or B squared? Really inconsistent with how I denote these as being multiplicative or additive. I'll do b squared, but this is just all the even powers of b. So this is still isomorphic to z squared, because this is still isomorphic to a copy of z. But the point is the index of this subgroup is 2. This is an index 2 subgroup. And this is a 2-sheeted cover of the torus. Now, can you show me what would be the fundamental, what would be the cover that corresponds to a squared? What would that look like? How are we going to do it?
You open up a circle along it.
Yeah. So like down here, it will cut it like a bagel, right? So maybe I need a new color to be my cutting color. But we're not going to cut all the way through the torus. We're just going to like trim the outside. Right? Because if you trim that, what are you left with? You can now unfold it and you get either an annulus or a cylinder. Do you see that? Like this is the same as, let me try and draw it. Kind of imagine unfolding it. Do you see what I'm trying to go for here? Where this yellow circle is what I had just cut. So I have the top and then the bottom. Okay, so I have this weird like cylinder or annulus shape. You could also think of this as being flat in it, to be like an annulus. Where, if you take this outside rim and you fold it to the inside, you get your torus. Okay, in this case, that hole would be in the middle, but you could pull it out like this, and then you get that picture. Okay, so what's the map up here? What's this space? It's still a torus, but how should we think of it? Well, it's like 2 of these glued together, right? So it's like you glue one on top of the other one, which now it really is cutting like a bagel. Something like this, where you have the top half and the bottom half. So this might be a little bit hard to see, but I'm saying you have the top half of, trying to draw the top half of a donut. The top half and there's a hole here. And they glue up together to give you this, where these guys glue together to give you that. You see what's going on? Okay, cool. So now, whereas down here, if you had a single circle A, let's say meets right here, you're going to be going twice around your A. This would become A squared. Whereas here, you just had a single A. And over here, a single time around for B is still, this B is now still a single B. So this is another way that you could have a 2-sheeted cover. Or you could easily have a 5-sheeted cover like this, where you just slice it in 5 pieces. Or you could have a 5-sheeted cover like this, where you slice it, well, you have to imagine gluing together several of these. It's a little bit harder to imagine, but. So what if I wanted to mix and match? What if I wanted to draw a picture of a cover such that pi 1 of this cover looked something like a cubed b to the 5th. Well, you can tell my artistic talents are limited, right? So maybe someone could do this, but I'm limited. So what I'm going to do is I'm going to represent the torus in a slightly different way. I'm going to represent the torus as just being a square, where I glue the bottom to the top and the left to the right. I'll call this bottom arc A. So this guy on top is also A. And I'll call this top arc, or this right and left arc B. What I want you to notice is that this first representation here is much the same, except you had 2 copies of the B. So how could that be possible? Well, it's like that guy, except for this guy, you glue 2 of the squares together, where you had, so these all get glued to the same base point, where you have your B and your B get glued to another copy of B and B. So you actually have B squared going up. And then you have a copy of A going over. And you were just mapping this down to that square. In this case. In this case, you were just gluing to this direction. So that's why you had, sorry, these are not the same base point. These 4 base points get glued together. This is some other base point. Here, you think of this as being A with another copy of A. On top and bottom glued together. And here, B with another copy of B. Glued, mapped down there. So what's the mapping? It's the mapping that sends like both of these 2 points down to that single point, right? So if I want to do something like this, I just map, if you think of this as like a 1 by 1 cube, up here I have a 3 by 5 cube. So let's see if I can fit 5 in. 1, 2, 3, oh no, 4, hey, there we go, 5. 1, 2, come on, 3. Nice. Something like this, right? Where here you have 3 copies of A. 3 copies of A going over, and 5 copies of B. Now, when you glue this all up, this is still just a torus. You just get a big torus. But what you can think is it's like all of these points are mapping down to this point. So you tell me now, what's the universal cover? Good. So the universal cover is where you don't want any loop. So instead of going 3 or 5 or any distance then coming back, you just go forever without looping back. So what's the universal cover of the torus? Well, if I think of the torus as the square with sides glued together, the universal cover is just taking this infinite grid of squares, where if I think of this as being like R2, and I think of this as being like the map of like 0, 1 cross 0, 1, then you'd have some point here, whatever this point here is. Maybe it's like, I don't know, maybe this is like at the point 5.7 and like 3.8 or something, would just map down to the corresponding point here, which is the point 0.7, 0.8. And all of the 0.7s and 0.8s would be pre-images. You'd also have up here the point 5.7, 4.8. That also maps down there. And all of these, here you'd have 4.7 and 4.8 would also, all of them would map down to this point. All of the integer points, integer lattice grid, would map to your base point. So you can think of R2 as being the cover of your torus. Maybe in the last minute. I mean, this is, I gave you this abstract definition of covering space. This is actually how we think about it, is with these gluing operations. In the last minute, you tell me, how in the world could we think about the universal cover? This is my universal cover. Notice it's simply connected. Any loop in here is contractible. What is my universal cover for the two-hole torus? Do you remember how we can represent the two-hole torus? An octagon. It's an octagon. With some gluing directions where it's like A, B map onto A inverse, B inverse. These are going the opposite way, and then you have C, D, and then going the opposite way, C and D. So how are we going to build the universal cover of this guy? Well, it should be just like we glued all these squares next to each other. It should be a bunch of octagons. Okay, so we should tile the plane with octagons, right? So do it, like here is such a tiling of the plane with octagons. Okay, so these have now 6, so you need, let's make these split a little bit more. Okay, this is this like fractal thing again where I have to draw it for 25 minutes. Okay, anyway, that's enough. And then here now it's 6, 7, so that makes an 8th one, right? So let's partition these out. 2, 4, 6. Oh, 2, 4, 6. Oh, that already had 6. So there's my 8th one. Here's my 8th one here. Okay, and you just keep going, right? With this tiling pattern. Now, you can't do this in R2. But 2, 4, 6, 7, so this is 8. But you do have such a tiling in hyperbolic plane. So you can tile the hyperbolic plane with these octagons, and it then becomes a universal cover for the two-hole torus. Okay, cool. We'll stop there.